All right. Welcome to 6S081 Operating Systems. I'm Robert. I'll be co-lecturing with Franz and David and Nicholas are the TAs. Please, during these Zoom lectures, ask questions. You can either interrupt me by audio or enter something into the chat window, and one of the staff will see and ask a question for you. By the way, we'll be recording these lectures and we'll post the recordings later so you can review them, or for people who can't make this time, so they can nevertheless see the lectures. All right, I want to start by laying out some of the goals of the course. So number one is to understand the design and implementation of operating systems. And the design is sort of high-level structure, and implementation is really about what the code looks like. And we'll be spending a lot of time with both. And in the interest of getting a deep understanding of what's going on, you'll get hands-on experience with a small operating system, the XV6 operating system. And in addition to actually looking at an existing operating system, you'll be in the labs, get a bunch of experience extending the operating system, modifying its, improving its behavior, and writing system software that it uses the operating system interface as if it were an application. So this is what you're going to be doing in the course. We're also interested in what the purpose of the operating system itself is, as well as of the course. So for that, I have a sort of list of a couple of things which, even though there's lots of different operating systems out there, they typically have a common set of purposes. One of them is to abstract the hardware. That is, what you're given typically as a kind of starting point is you buy a computer. The computer has a CPU and memory, but that's a very low level set of resources. It's fantastic to have much higher level interfaces and abstractions that applications can use, such as processors or file systems, both for convenience and for portability. Another very important task of an operating system is to multiplex the hardware among many applications. You might be running a text editor and a compiler, or maybe multiple different database servers or something on your operating system. It's fantastic to be able to have the operating system run both of them at the same time, or all the things that are going on at the same time without having them interfere. So that's often called multiplexing. Because there may be a lot of things happening on the operating system at the same time, it's critical that they not interfere unintentionally, even if they have bugs. And that's task is called isolation, the idea that different activities should not be allowed to interfere. On the other hand, there are times when different activities would like to interfere or would like to interact or cooperate. So for example, if I create a file with a text editor and I'd like my compiler to read the file, we definitely want to allow that kind of sharing. So we want to allow sharing when it's sort of what the user has in mind. But in many circumstances, the user doesn't want sharing. Maybe you're logged into a time-sharing machine like Athena, and you don't want other people to read your files. So we also need, as well as sharing, we want to not share when we don't want to, which we could call security or a permission system or an access control system. Another thing that people value in operating systems is if you spend a lot of money on hardware on a computer, you'd like your application to be able to get the sort of full performance that the hardware ought to be able to provide. And a lot of that is just application programming. But inevitably, unfortunately, some of it is the operating system has to make sure that whatever services it provides don't get in the way of applications getting high performance. So you want to at least not get in the way and maybe even help applications achieve good performance. Finally, with most operating systems, have to support a wide range of different applications. Maybe it's a laptop running a text editor, maybe it's running games, maybe your operating system needs to support database servers or cloud computation. And usually, because operating systems are quite expensive to design and build, people use the same operating systems for many different tasks. Like Linux, for example, which I'm sure many of you are running, is used in all of the situations I mentioned. So the same operating system really has to be able to support a range of often quite different uses. So we're hoping to be able to support sort of all these different goals simultaneously. And we'll hear more about all of them during the course. All right, operating systems, sort of people have worked out a set of design ideas over the decades that have worked pretty well, sort of ways of organizing things. And I'm going to lay out for you the sort of classic organization. It's sort of the standard deal for this course, and is actually quite common around for many operating systems. So this is sort of, OS internal organization, or the way I think about it is in terms of draw a box for the computer. The computer sort of comes with a bunch of hardware resources, which I'll put at the bottom. Maybe there's CPU and RAM and a disk for storage and maybe a network interface. So this is sort of hardware that's the lowest layer. Sort of at the top, we want to run various applications, maybe a text editor. I happen to use VI as a text editor. Maybe you're going to run a C compiler, say CC. Maybe you run lots of other things. We're going to talk a lot today about the shell, which is the command line interface. So we have all these different programs that are running. And this is the sort of world in which applications run, is usually called user space. And as distinct from that, there's a single program, a special program that's always running called the kernel. And the kernel is sort of the guardian of the resources of the computer. It's what first boots up when you turn on the computer. There's just one of it. It maintains data to help it manage each of these processes. And the kernel also maintains lots of data structures to help it interface and all the different kinds of hardware that these user programs need to use. The kernel also has built in a bunch of services. And so, for example, there's typically a file system implementation inside the kernel that implements things like file names and file contents and directories, and understands how to store the files in the disk. So your programs are going to talk to the file system inside the kernel, and the file system implementation is going to talk to the disk. And in this course, what we mostly focus on is all the things that has to happen inside the kernel, and on the interfaces between user programs and the kernel, as well as the sort of structure of the software inside the kernel. So we care a lot about these services inside the kernel. One of them is the file system I mentioned. There's also management of processes. Each of these running programs is called a process, and it has things like its own memory, for example, as well as a share of the CPU time. So the kernel manages processes as a kernel service. The kernel manages the allocation of memory. The different processes need different amounts of memory. The kernel multiplexes and divides up the memory, allocates the memory among all the different processes. The kernel, as I mentioned, influences the file system. The file system really comes in two or three logical, or a bunch of logical parts, but for now we can think of it in terms of managing file content. That's what's inside files, figuring out where on disk each file's content ought to live. The file system also somewhat separately manages a namespace. Each file has a name, and there's a hierarchy of directories. Every directory has a bunch of files in it. All that's managed by the file system. There's typically some sort of security arrangement. Maybe we'll call it access control. by which the kernel decides that, when a given process wants to read, use some resource, maybe read something from the disk or use some memory, the access control machinery inside the kernel is what gets to decide, yes, is that allowed, is that not allowed? And that can get pretty complicated if we're talking about time-sharing systems like Athena systems, where there's, each of these processes may be run by a different user and have different access control rules applied to what it's allowed to get at. And in a real full-blown operating system, there's turns out to be many, many other services. There's typically some way for different processes to talk to each other called inter-process communication. There's typically a whole bunch of software associated with the network, things like the TCP IP protocols for talking to the network. There's typically support for sound cards. There may be drivers for hundreds of different disks and hundreds of different network cards. So in a full-blown operating system, there's huge amount of stuff here, and this may run to millions of lines of code inside the kernel. So that's sort of a quick overview of what's inside the kernel. We're also interested in how applications interact with the kernel and what that interface looks like. The usual, so this is the API for the kernel, how applications get at the kernel. Typically that's done with something called system calls. And these are things that look like function calls that programs can make, but actually jump into the kernel and execute a system call implementation in the kernel. I'll talk a bunch about that in the latter part of this lecture. For now, just to give you a flavor, here are what a couple of different system calls might look like in the source code of an application. One might be that if an application wants to open a file, it calls the open system call and tells the open system call the name of the file. So maybe it wants to open a file for writing called out, and there'll be an extra argument here saying, one in this case saying I want to write that file. And so this thing that looks like a function call, if opens the system call, is actually special code that jumps into the kernel, and the kernel can retrieve these arguments, executes some kernel code that implements open, maybe talks to the disk, and then returns a value, and that's this file descriptor. This FD stands for file descriptor, which is the program can then use as sort of a handle to refer to this open file. If you want to write to a file, the system call to do that is called write. You have to pass it one of these file descriptors, the same as was returned by open. These are now arguments that are passed in the system call from the program into the kernel. You give it a pointer to a buffer of characters. So an easy way to do that in the C programming language, which these examples are written by, is with double quotes, and then the string, the bytes of the string, this \n is a new line, and the third argument is the count of characters that you want to write. And so this really gets passed as an address in memory. And so you're telling the kernel, look, please write 6 bytes from this address to the file that this file descriptor refers to. A much more exciting system call that you will encounter is the fork system call. Fork is the system call that creates a new process, and it returns, actually creates a process that's identical to the caller, and fork returns an identifier, the process identifier, or PID, of the new process. It's actually a little more complicated than that, and we'll hear more about this. So again, these are all look like function calls, but the system calls are special because they jump into the kernel. That's just a taste. We'll see more later. With that as a sort of quick overview, I want to just mention why I find the study of operating systems to be both challenging and interesting. Why it's maybe intellectually worth taking a course in this area. So one reason why it's hard is that the environment's unforgiving. The programming environment inside the kernel is unforgiving, because when you're programming, when you're modifying the kernel or extending the kernel or writing a new operating system kernel, you're providing the infrastructure that everybody else assumes is already present to run their programs. right? And everybody else gets an operating system under their program when they write ordinary application programs. But when we build operating systems, what we get is the hardware underneath our operating system, which turns out to be more difficult to deal with. In this course, we get to use a hardware simulator called QEMU that simulates a CPU and a computer, and that makes life a little bit better. But yeah, it's still a kind of a difficult environment to program in. Another reason why it's hard and interesting is because if you're designing an operating system, you have to satisfy a bunch of tensions that require real design thought. So one is that you'd like your operating system to be both efficient, which often means that it sort of operates at a low level close to the hardware, but for ease of use, and because real live people have to write programs that use your operating system, we'd like it also to be provide abstract, high-level, portable interfaces. And it's a neat trick to provide abstract interfaces that are simple and portable, but that are also efficient. Another tension is that we'd like to provide a very powerful operating system services so that the operating system can shoulder a lot of the burden of running programs. So we'd like the powerful operating system services, but we also want to have simple interfaces. That is, we don't want tremendously complex, hard to understand interfaces for programmers to use, because then they're not going to understand them and they may find it hard to use. So this is really simple API. And so this is possible to do, to provide simple interfaces that have powerful machinery inside them. And so we'll always be searching for sort of simple interfaces that provide powerful services.
Hey, Robert, we have a question in the chat. What is unique/different about saying system calls jump into the kernel, i.e., as opposed to a standard function call that jumps to another function?
Well, the kernel's a piece of code that's always resident, that has special privileges that because it booted the machine booted the kernel has special privileges. It can get directly at all kinds of hardware, like the disk device, that ordinary user programs can't get at. So if you make an ordinary function call, the function you're calling doesn't get any special privileges with respect to the hardware. Whereas if you make a system call into the kernel, we'll talk about how this works, but that ends up when the system call jumps into the kernel, the system call implementation in the kernel then gets all these special privileges so that it can modify all kinds of sensitive and protected hardware resources, like, for example, getting directly at the hard disk. We'll see a lot more detail for all of this shortly. Okay, so a final tension that that all operating systems need to satisfy is you want to give programs as much flexibility as you can. You don't want to constrain them. So you want to have very flexible interfaces, but you do need to constrain programs somewhat because you absolutely have to have some notion of security. You can't, we love for programs to give programmers complete freedom, but it can't be complete, can't be really complete, because we don't want programs to get directly at the hardware or to interfere with other programs, or to sort of be able to interfere with the operation of the operating system itself. And so these are all, it's possible to do a good job, and we'll talk a lot about it, but it's always a bit of a puzzle to provide sort of both of these, the properties in both of these columns. Another thing that makes OS design hard and interesting is that operating systems provide a lot of features and a lot of services, but they actually tend to interact, and sometimes in odd ways that require a lot of thought. So even in the simple examples I gave with open and fork, those two interact actually. If a program allocates a file descriptor with the open system call, and then that same program forks, and the semantics of fork just turn out to be that you create a new process that's a copy of the current process. This file descriptor you opened, if that's truly to be a copy, this file descriptor still has to be present and usable in the child. And So that has to be thought through. That is, the open and filed descriptors interact with fork in this interesting way. And somebody has to figure out, oh, should the child be able to get at the file descriptors created before fork was called? And the answer happens to be yes, in the operating systems we're going to look at. All right, and so other things that turn out to be interesting, I already mentioned that operating systems have to cater to a wide variety of uses. The same OS used both for database servers and smartphones, for example, and operating systems. As time goes on, the hardware that you run, the hardware you get with typical computers changes. Maybe you get super fast SSD storage instead of mechanical hard drives, for example. And about 15 years ago, multi-core computers went from being rare curiosities to being pervasive. And recently we've seen order of magnitude speed-ups in how fast networks operate. And so all these require rethinks periodically of how operating systems are designed. Now, so those are sort of intellectually why you might take the course. There's also some maybe more practical reasons why you might be glad to have taken this course. One is if you're interested in what happens inside computers, what goes on under the hood, sort of in secret when you turn on your computer, this is a good course to take. Similarly, if you like infrastructure, that is, if you enjoy building sort of services that other programs can then use, this is, of course, essentially all about infrastructure, because that's what operating systems are. If you ever need to spend a lot of time tracking down bugs in application code or tracking down security problems, often that involves understanding what was going on inside the operating system, because it's ultimately the operating system that enforces a lot of security, and when things go wrong, it's sort of the operating system that has to pick up the pieces. So that's often involved in tracking down bugs. And finally, yes.
We have two more questions from the chat. So the first is, how important is it for application developers to truly deeply understand the operating systems they're developing their applications for? Do they necessarily need to be experts?
You don't have to be an expert, but if you spend a lot of time developing and maintaining and debugging applications, you'll eventually end up knowing a lot about the operating system, whether you meant to or not. It just comes up, and you're often forced to understand.
And the second question is, do high-level programming languages like Python use system calls directly, or are there built-ins / wrappers for convenience?
A lot of high-level languages are sort of at one remove from system calls. That's absolutely true. So partially because a lot of languages want to provide a portable environment that works on many different operating systems. So they can't necessarily commit to the specific system calls of any one operating system. So the answer to the question, I think, is if you use Python, you're somewhat insulated from the system call interface. Internally, of course, Python has to make system calls to get its work done. And certainly in Python and in many other languages, there is usually a way to get directly at the system calls of whatever your operating system you're running on.
And folks, for questions, you can just feel free to jump in yourself and ask questions. You don't need to go through the chat.
Okay. All right. Sorry. I'm going to spend a couple of minutes now talking about the class structure of 6S081 before switching back to actual technical content. So there's a website for the course, which I don't want to write out just now, but it's you can find it by looking for 6S081 on Google. And the website has the schedule, it has the assignments on the schedule, it has the lab assignments, and it has the sort of information about course structure, like the grading policy on it. The other big resource you're going to want to keep track of is Piazza. I guess everybody who's here got here by way of Piazza, but as well as, so we use Piazza really for two main things. One is as a way of people being able to ask questions about the lab assignments and the course staff will try to answer these questions, but you should feel absolutely free to answer each other's questions as well. And the other big thing that happens on Piazza, if there's announcements, if there's any announcements about the course, we'll put the announcements on Piazza. So you should keep an eye on Piazza for announcements, even if you're not using it for lab help. One of the big parts of the course is these lectures. The lectures will cover basic ideas on operating systems. Some of the lectures will be devoted to detailed study of the code in XV6, which is our small teaching operating system. And so talk about how it works. We'll look at the code and sort of show the code executing during lectures. And in addition, before many of the lectures, there'll be assignments, reading assignments from a book that sort of describes how XV6 operates and why it's designed that way. So you should do the readings before the class so that you'll understand the discussion in the class. Some of the lectures are devoted to background to help you do the labs. Sort of explanations of how C works, of how the RISC-V, which is the microprocessor that we'll be using, that you'll find helpful in understanding how to do the labs. And towards the end of the course, we'll spend some lectures discussing some operating system papers, research papers, and some classic papers in the field, which we'll ask that you read before the lectures, and then we'll sort of talk about the papers during the lecture. For all the lectures, or almost all the lectures, we ask that you submit a question about the reading for the lecture before the actual time of the lecture, which many or all of you did for this lecture, for which thank you. And we will read those questions to help us guide us about what to talk about, and we'll try to answer as many of the questions as we can, although there's rarely time, unfortunately, for us to answer all of them. The next big part of the course are the labs. There's a programming lab due almost every week. And the point of the labs is to help you get hands-on experience with implementing and using operating systems. The lab that's due next week is actually about about writing applications that make the system calls we'll be talking about. Whereas most of the labs after that involve you either implementing basic operating system features or adding kernel extensions to the XV6 operating system. The very last lab is one in which you'll actually add a network stack and a network driver, so you'll be able to connect in over the network to the operating system that you run. You should, if you have problems with the labs, there'll be office hours that the TAs will hold. In addition, you can post questions to Piazza, and very often you'll be able to get useful answers from Piazza more quickly than from office hours. We welcome you discussing the labs, talking about the labs, talking about how to design the lab solutions, but we ask you, please do not look at other people's solutions for the labs. Please, all the code you write should be your own, and you shouldn't share code or look at other solutions. The grading for the course will be mostly determined from the labs this year. So 70% of the grade will be based on whether or not that the lab you submit passes the tests. And for grading, we run the same tests that we supply you. So if your lab passes all the tests that we give you, then chances are you get full credit for the lab. 20% of the grade is going to be from lab checkoff meetings. For each of you, we'll pick a couple of randomly selected labs, and one of the TAs will talk to you and ask you questions about your implementation, just to make sure that you really understand what's going on. So this is the lab checkoffs. There's 10% remaining. Is there a question?
Will the lab checkoffs kind of be like a yes or no, 1 or 0 type of thing, or would they be like, could someone get, like, if they answered some of the questions right but not all the questions right, would they get in between for their grade?
I haven't thought this through. There's certainly room for partial credit, but
it won't be binary. it'll definitely be, you can receive partial credit.
Okay.
The last 10% is going to be driven by the homework and participation during lecture and in Piazza. There'll be no exam or quizzes this year. And so what that means is that most of the, 90% of the grade is being driven by the labs. So you should spend a lot of time in the labs, make sure that you start early and have enough time to complete them and work out bugs in order to get full credit. And as a result of that, this is going to be a very kind of hands-on, software-oriented course. All right, any questions about the machinery of the course?
We got a couple questions in chat. So the first is a logistical question. Currently 6S081 isn't listed as usable for the systems concentration in the MEng. Are there plans to add it to the list of classes later? I think for that, because it's not an AAGS, it's an AUS, it can't be used to fulfill MEng requirements as it's not a graduate level class. But and then we have, is the only homework to submit questions looking at the calendar? That appears to be the case.
Unless I'm forgetting something, I think that's the case, yes.
So are there going to be cutoffs for grades like X% gets an A, Y% gets a B, etc.?
No. We're going to try to, for each student, estimate our impression of how well you've understood the material and assign a grade based on that. So there's no predetermined cutoffs. All right, anything else? All right.
Just real quick, for folks in the chat asking about the concentration requirement, I'm not 100% certain, but 6S081 is not, it's like a temporary number before the class gets an official one, so it certainly won't be listed anywhere. If you needed to fulfill a concentration, I think your best bet is probably to fill out a petition or to email somebody like Katrina LaKurtz to see what the status is. We don't control, what classes fill these kind of requirements, unfortunately. And for what language we'll be using, the class will be in C.
All right. All right. For the rest of the lecture, I want to talk about what system calls look like to applications. And since the system calls are the interface to the services that the operating system provides, it's actually pretty important what those system calls look like, what applications expect from system calls, and how they behave. So it's sort of worth understanding what the interface looks like. You'll be using the system calls we talk about in the first lab, and extending and improving the internal implementation of these system calls in subsequent labs. What I'm going to do is show some simple examples of little programs that call system calls, and then I'll run them in XV6 for you. I'm going to run them. The XV6 is it's a simplified Unix-like operating system. And Unix is an old operating system that's sort of at least intellectual basis for many present-day operating systems, such as Linux and OS X. So it's in very common use. XV6, our teaching operating system, is much simpler. It's sort of inspired by Unix and has the same overall structure, but is dramatically simpler than any real Unix operating system. And it's simple enough that hopefully, it would be relatively straightforward for you to read all of the source code as well as read the book in a couple of weeks, certainly during the semester, in order to kind of understand all of what happens inside XV6. XV6 runs on the RISC-V processor, RISC-V microprocessor. And this is the same microprocessor that's the focus of recent 6004. So many of you may actually know quite a bit about the RISC-V instruction set. In theory, you could run XV6 on top of a RISC-V computer, and people have done that. But we're going to run it under the QEMU machine emulator. So just to write this down, we got our operating system is XV6. It runs on RISC-V microprocessor. And not just RISC-V microprocessor, but we assume a certain amount of surrounding hardware like memory and a disk and a console interface for us to talk to it. But we actually run under the QEMU machine simulator, so that which runs under Linux, so that all of you can actually run XV6 without having to have hardware. Okay, so I'm going to switch to showing you code. All right, so first thing is I've set up XV6 on my laptop, and I'm going to run it. I'm going to type make QEMU, which you'll find yourself doing quite a bit during the labs, which compiles XV6. It's written in C, so it's compiled with a C compiler. Actually, maybe I'll make clean for you so you can see the actual compilation. And I type make QEMU, which has the effect of compiling and building XV6 kernel and all the user processes, and then running them under the QEMU emulator. It takes a moment to run the compiles. And now we're up and running XV6. And the $sign prompt you see is the shell, which is the command line interface to XV6, modeled after the shell in Unix, which is, if you log into a Athena workstation, it's like the shell that Athena shows you. XV6 is itself tiny, and it comes with a small number of utility programs, and including, for example, the ls program, which I'm about to run ls, and it gives me a list of all the files in XV6, of which there are only about 24, including things like grep and kill and make dir and rm, which may be familiar to you as Unix utilities. Okay, the first program I'm going to show you to illustrate system calls is a program called copy. And here's the source, it's just a page. And so what you're seeing here is a program that starts on line 8 at main. There's that sort of convention for C programs. It sits in a loop at line 12. And over again, it reads some data as input and on line 13, and then writes the data it just read to its output on line 16. So if I run copy in XV6, just waiting to read input. If I type some input, it reads it and spits it back out to me. So it's a very simple program, it just does I/O. It's written in C, as I mentioned. If you don't already know C, it's worthwhile getting the standard C programming language book by Kernahan and Ritchie. And I think there's a more full reference to it on the course website, which explains to you in a very straightforward way how to program in C. As I mentioned before, read and write. This program makes really three system calls. Read, write, and exit are system calls. If you look at the call to read on line 13, it takes 3 arguments. The first argument is a file descriptor, which is really a reference to a previously opened file. And the shell ensures that when a program starts, by default, its file descriptor 0 is connected to the console input, and its file descriptor 1 is connected to the console output. And that's why I was able to type to this copy program and see the output. Of course, these file descriptors are expected, the program expects these file descriptors to have been previously opened and set up by the shell for it. And this 0, 1 file descriptors is a pervasive Unix convention. Many, many Unix programs expect to read in file descriptor 1 and read in file descriptor 0 and write to file descriptor 1. The second argument to read is a pointer to some memory where the program is asking the operating system to read data into that address in memory. So that's the buff argument. And line 10 allocates 64 bytes of memory on the stack for read to read into. And the third argument to read is the maximum number of bytes that the program wants to read. And the size of buff says just maximum 64 bytes. So the read call reads up to 64 bytes from whatever is connected to file descriptor 0, and that was my terminal in this example. The return value from read, it either may return the number of bytes read, which would be 6 in the case of me typing XYZZY. Read might be reading from a file. If it gets to the end of the file and there's no more bytes, read will return 0. And if some other error occurred, like the file descriptor doesn't exist, read may return -1. And so in many of these examples, like on line 16 there, my example code doesn't check system call returns for errors, but you should be more careful than me. You should figure out how system calls reflect errors. It's usually a -1 return value, and check all system call returns for errors. And if you want to know what the system call arguments and return values are, there's a table in, I think, chapter 2 in the book that explains all of the XV6 system call arguments and return values.
The question regarding the read syscall. What if we set the max read bytes to size of buff to 1 plus size of buff or bigger? So what if we try to read more than the size?
Yeah, then if there was 65 bytes to read, then the operating system would happily, well, just copy those 65 bytes to the memory that you provide. And of course, there's something else on the stack up there, maybe the return program counter or an argument or something. And so if you pass 65, then you're inviting the kernel to write junk to an unexpected place in your stack. And so that's a bug, and it may cause your program to crash or do something else unexpected. So as a programmer, you have to be careful here. There's nobody writing in C with these kind of interfaces. It's very, very easy to write code that the compiler is happy with and will run, but absolutely does the wrong thing. So that's too bad, but it's the way it is. Okay, one thing to note is that this copy program and indeed the read and write system calls, they don't care about the format of data they're reading or writing. They just read and write, and this copy program just deal with 8-bit bytes, with streams of 8-bit bytes. How you interpret them is totally up to the application. So the application may be parse these as data records or as C source code or who knows what. But the operating system it only thinks in terms of a stream of 8-bit bytes. Okay, so copy assumed, this code, my copy program assumed that the file descriptors were already set up, but we need to have a way to create file descriptors. And the most straightforward way to do that is with the open system call. And so here's the source for a program that called open that uses the open system call.
A question from the chat. Okay. What do you mean by a stream of bytes?
I just mean that if a file contains a bunch of bytes, then successive, supposing a file contains 1,000,000 bytes, if you make a sequence of read calls each for 100 bytes, you'll just read the first 100 bytes and then the second 100 bytes and then the third 100 bytes. That's all I mean. All right, so this program called open, first I'll run it for you. What it does is creates a new file called output.txt and then writes some bytes to it. And then it finishes, so we don't see anything because it wrote data to this file at open, but we can look at this output.txt file that it created and see the 000 that it wrote there. So line 11 in the program makes the open system call, gives it a file name, output.txt, and the O underscore stuff in the second argument to open are flags that tell the open system call implementation in the kernel that we'd like to create a file with this name and that we're going to write it. Open returns a newly allocated file descriptor. The file descriptor is just a small number, it's probably 2 or 3 or 4 or something. And then we pass that same file descriptor to write along with a buffer and a number of bytes to write. And that writes data to the file that the file descriptor refers to. What that file descriptor is actually doing is indexing into a little table inside the kernel. The kernel maintains state for each process that's running, each program that you run. And among other things, the kernel remembers a table for every running process of indexed by file descriptors. And the table sort of tells the kernel what each file descriptor refers to. A critical point is that each process has its own sort of space of file descriptors. So if we're running 2 different processes, 2 different programs in different processes, and they both open a file, they may actually get the same number back as a file descriptor. But because the kernel maintains a separate file descriptor for each process, the same file descriptor number may refer to different files in different processes. Any questions about open, about this little program?
We got a question in the chat, a question from someone not familiar with C. How are these files being described different from normal C programs? Is it because we're only using kernel calls, i.e. couldn't we also open or write a file in Python?
I don't think I understand. It's a C program that's opening and writing a file. Okay, I think I'm going to move on. All right, so you might ask what actually happens when...
I think maybe the question is whether someone is doing it in C any different than doing it in Python minus the syntax?
Well, it's not really. There's certainly ways to, I mean, Python provides nice function calls for opening and doing all these things for opening files, for example, and reading and writing files. There's sort of a layer of, there are somewhat higher level functions typically, not, pointers to memory, for example. And Python does more error checking for you. But when you open a file in Python or write a file in Python, the Python calls you make boil down to system calls just like these. Is that a good answer?
I think so.
All right. All right. All right. I've been over here talking to the XV6's Unix-like shell, and the shell is what people often call the command line interface, as opposed to some more graphical user interface. The shell turns, if you haven't used the shell turns out to be a pretty useful interface for things like system management of Unix systems. It provides a lot of utilities for messing around with files and for programming development and for writing scripts to do all these things. So you saw me before run, I just want to demonstrate a few shell features. Ordinarily when you type things, you're telling the shell to run a program. So when I type ls, what that means is I'm asking the shell to run the program whose name is ls. And what that really means is there's a file in the file system called ls that contains some instructions, some machine instructions, and I'm asking the shell to run the instructions that are in the file called ls. I'm going to run ls now. Ls, what it actually does is get a listing of the files in the current directory. And you can see up there on the 4th line that Among the other files that ls says exists in its list is a file called ls, which is in fact the file containing the instructions I just ran. The shell does a few other things for you other than running programs. It allows you to redirect I/O. So for example, if I say ls greater than out, what that means is I'm asking the shell to run the ls command, but with its output redirected to the file called out. And I run ls. We don't see any output because the output all went to out. Now out contains a bunch of data. The cat command reads a file and displays the contents of the file. So if I say cat out, I'm just going to see now this is the saved output of ls. You can also run a command like grep, and I can give it an argument x. And what grep x is, the grep command searches for patterns. Again, if I run grep x, it's going to search for lines of input that contain x. I can tell the shell to redirect its input from the file out in order to look for instances of x in that saved ls output. And it turns out there's 3 files whose names contain x's. We're going to spend a bunch of time with the shell. The shell is sort of the most traditional and fundamental interface to Unix, because when Unix was first developed, all there was simple terminal interfaces like the one we're using. And the main use of Unix originally was time sharing, a bunch of people logging into the same machine, much like Athena, and talking to shells.
A question about system calls and the compiler. How does a compiler handle system calls? Does assembly generated make a procedure call to some code segment defined by the operating system?
There's a special RISC-V instruction that a program can call that transfers control into the kernel. So indeed, when you write C code that makes the system call like open or write, I mean, technically what actually happens is open is a C function in the C library, but the instructions in that function are really machine instructions. It's not, open. The open function that we're calling isn't a C function. It's implemented in assembler, and the assembly code consists of this special instruction. It's actually called ecall on the RISC-V, the special instruction that transfers control into the kernel. And then the kernel looks at the process's memory and registers to figure out what the arguments were. All right. The next example I want to look at is an example program that calls fork to create a new process. So this is the very simple use of fork. At line 12, we're calling fork, and what fork does is creates a copy of the memory of instructions and data of the calling process. Now we have 2 processes with identical memory. The fork system call returns in both processes. In the original process, the fork system call returns the process ID, which is an integer greater than 0. In the original process, fork returns the process ID of the newly created process, and in the newly created process, fork returns 0. So we sort of break, even though the processes have identical memory, we kind of break the symmetry of old versus new process by the return value from fork. And in line 16, you can see code that checks and says if the process ID is equal to 0, it must be the child. We must now be running in the child. But of course, there's 2 processes, and in the other process, in the calling process, which is usually called the parent, the process ID is greater than 0. So the child will print child, and the parent will print parent. And then they'll both exit. So when I run fork, here's what we get. So it may look like garbage, but what's actually happening is that after the fork, both of these processes are running. They're both running at the same time. And QEMU is actually emulating a multi-core microprocessor for me. So they really are running at the very same time. And so when they produce output, they're producing each byte of their output at the same time as the other process is producing the corresponding byte of its output. So the outputs in the 2 processes are interleaved. You can see this, they're both typing F. They're both going to type fork returned. So you can see the F from both of them, and the O for both of them, and the R for both of them, and so on. One of them, you can see the 0 at the end of that first line is in the child fork return 0. And I'm guessing that in the parent fork return 19, that is the child's process ID is 19. Under XV6, that basically means the 19th process that was created since boot. And then one of them prints child, and you can see the CHILD, and interleave with that is the other one printing parent. So, this is sort of a silly use of fork, but we can see sort of vividly in this output that it's created two processes that are, and both of them are running. Fork returning both processes, and they're both running. But also note that one printed child and the other parent. So it's important that fork returns differently in the two processes.
Good question. Is the child process as a result of fork always identical to the parent process, or could they be different?
In XV6, they're identical, except for the return value from fork. So the instructions are the same, the data is the same, the stack is the same, and also both processes, the processes are copies, and they both have their own separate address spaces. That is, they both think that their memory starts at 0 and goes on up from there, but it's different. It's different memory for the two of them. In a more sophisticated operating system, there are some details which we definitely don't care about. They may occasionally cause parent and child to differ, but in XV6, they're the same except the return value. So the memory is the same. In addition, the file descriptor table is copied. So if the parent had some files open, then the child sees the same set of file descriptors. Although the child is seeing them in a copy of the table of file descriptor information. And so we'll see in a moment that it's quite important that fork copies the table of open file descriptors as well as the memory. Okay, so fork creates a new process, but when we run stuff in the shell indeed creates a new process to run each command that you type. But it needs to actually run the command in it. So, if I type ls, the shell forks to create a process to run ls, but there needs to be some way for that new process to actually run the instructions from the ls program. To load those instructions from the file called ls. And the example program I'm going to show you in a minute uses echo. Echo is a very simple command that just takes whatever arguments you pass to it and writes them to its output. And I prepared for you a program called exec, which makes the exec system call, which replaces the calling process with the instructions read from from the file you specify, and loads the instructions from that file over the current process, sort of discarding its current memory, and then starts executing those instructions. So the call to exec, the system call exec on line 12, is going to have the effect of the operating system loading the instructions from the file called echo into the current process, sort of replacing the memory of the current process, and then starting to execute those instructions. And in addition, you can pass arguments, command line arguments. Echo exec allows you to pass an array of command line arguments, which is just an array of pointers in C. Line 10 sets up an array of character pointers, which are essentially strings, and initializes that array to be to contain the strings echo, this is echo. And that's equivalent to running the echo command with the 3 arguments, this is echo. And so when I run exec, indeed, I see this output, this is echo, but even though I ran the exec command, the exec program, what the exec program does is call the exec system call to replace itself with echo. And so it was really the echo program producing this output. Something about the exec system call that's important for us is that exec preserves the current table of file descriptors. So whatever file descriptors 0, 1, 2, etc. were referred to before exec, they refer to the same thing in this new program whose instructions we've loaded. Another point is that ordinarily exec does not return because exec replaces the current process's memory entirely. There's nothing for exec to return to. So exec, reads the instructions from that file and executes them, and then that's it. The only time exec returns is if some error occurred that prevented the operating system from running that program for you. So for example, if the program doesn't exist at all, if exec can't find a file called echo, for example, then exec would return -1 to signal that something went wrong, it couldn't find the file. So ordinarily exec does not return. It only returns if the kernel couldn't actually run the file for you. Questions about exec?
One question in the chat is, what is the last 0 for in argv?
It marks the end of the array. C is so low level that there's no, the C array scheme doesn't have a way for code to find out how long the array is. And so to tell the kernel that, we meant that the array contains echo, this is echo and nothing more. We put a 0 as the last pointer. Each of those strings in double quotes is actually a pointer to some memory that contains those bytes. That fifth element of the array is a pointer whose value is 0. The convention is that a pointer whose value is 0, or what's called a null pointer, sort of signifies nothing, or that we're done. And so the code in the kernel is actually walks through this array until it finds an element whose value is 0. Okay. Right. So this is how a program can replace itself with another program from a file. But actually, when we run stuff in the shell, like echo ABC or ls or anything else, we don't want to replace the shell. We don't want to have the shell just call exec, because that would replace the shell with the echo command, and then when echo exited, that would be it. We don't want echo to replace the shell. So what the shell actually does is fork, and then the child calls exec. And that's an extremely common Unix idiom. There's programs that want to run a program but regain control. What they do is call fork and have the child call exec. So here's a simple example, this fork exec program. So in this program, call fork on line 12, and the child started at line 14. We call exec much like before. So the child process asks to replace itself with the echo command, and echo does this thing and then exits. And then the parent process regains control because when the fork returns the greater than 0 value in the parent process. So the parent process then continues to execute at 19, and Unix provides a wait system call at line 20 for a process to wait for for a child that it created with fork. Because when I run a command, here on the command line, we want the shell to wait for the command to finish before it prints the prompt again, before it prints this $ prompt asking me for more input. And so it's the wait system call that allows the process to wait for any of its children to return. And this status argument is a way for an exiting child to communicate one integer 32-bit value from the exiting child to the waiting parent. So on line 17, that argument to exit, that 1, that's the argument to exit, the operating system passes that 1 from the exiting child to the call to wait at line 20. So wait, the ampersand in wait is passing the address of the status variable to the kernel. The kernel fills in that address with the child's argument to exit. And the convention in Unix is that if a program completes successfully, it exits with status 0. But if it encountered an error, as at line 17, then the Unix convention is that you pass 1 to exit. And so if you care, the calling process can look at the status from wait and decide whether the child completed successfully or not.
Professor Morris, quick question.
Yes.
About the exec call on line 15. We mentioned not a bit ago that exec will completely go into the echo program and not return to fork exec. So would it ever reach line 16 and 17?
Well, not for this exact code, because there happens to be a program called echo. But you know, if I modified that code here, let me just modify this code for you. Okay, so first let me just run fork exec. Right, it actually does execute echo with those arguments. We see the output. This is echo, and we see the child exited to show that echo exited successfully, and the parent waited for it. Let me just modify the program for you. And instead of echo, I'm going to run some command that doesn't exist. Right. I actually have to exit out of QEMU with Control AX and then rebuild the whole thing in order to recompile my modified fork exec. And I run fork exec again after modifying and recompiling it. And this time, because the program we're asking to actually, the program we're asking to execute doesn't exist, exec does return. We see the exec failed output. And the exit 1, you see the 1 there is communicated back to the parent, which says the child exited the status 1. Right,
so exec returns back to the calling function when something went wrong?
Yes. Right. Okay, good. All right. Something to note here that actually I think many of you have already noted is that this is a common idiom here, this fork followed by an exec in the child. And it's potentially a bit wasteful. The fork copies the entire parent process, but exec throws away all that copied memory and replaces it with whatever is in the file that you're running. So, you know, if you're worried about this kind of stuff, the copy implied by the fork is in some sense mostly wasted because all that copied memory is just thrown away and replaced by the exec. And this effect actually would be significant for big programs. If you have a multi-gigabyte program that calls fork, and it did indeed copy all the memory, it would actually take a fair fraction of a second, perhaps, to do the copy, which could be a problem. But later in the course, you'll actually implement some optimizations, in particular something called copy on write fork, which will eliminate almost all of the apparent inefficiency of fork copying only to have exec throw away the copy. It turns out with a bunch of tricks involving the virtual memory system, you can build a fork that's lazy about the copy and that doesn't do, in the common case of fork immediately followed by exec, where you don't actually have to do the copy because the child doesn't actually use most of the memory. I think you'll find that's a fun and interesting lab.
Question from chat. Why does the parent process print parent waiting completely before the child calls exec?
It's just chance. The observation is that it could be that the parent's output could be interleaved with the child's output in the same way that we saw before with the simpler fork example. It just happens not to be. There's no guarantee that this is the output we would see. In fact, we shouldn't be surprised if we saw the lines of the output in the other order or interleaved. I suspect what's going on is that it takes a bit of time and effort. The exec system call is a little bit expensive because it has to load all those instructions. It has to access the file system and access the disk and read the contents of the file called echo off the disk into memory after allocating some memory, and that even after freeing some memory from the old process. So there's quite a bit of machinery involved in the exec system call. And apparently that takes long enough that the parent can complete producing the output before the exec is finished and started running echo. Does that make sense?
I have another question. Is it convention that the child can't wait for the parent?
There's not a way, Unix doesn't have a way for the child. There's no straightforward way for the child to wait for the parent. The wait system call is sort of the only mechanism available. Well, the wait system call waits for your children, and that's it. So what wait does is, if you have any children and one of them has already exited or does exit, then wait will return. But if you don't have any children, say because you are, because well, in this simple case, where it was just a parent and a child, if the child called wait, the child doesn't have any children, and in that case, wait just returns immediately with a -1 error return saying this process doesn't have any children. Anyway, the short answer is there's no way for a child to wait for its parent to exit.
And another question, when we say the child copies all the memory from the parent process, what exactly do we refer to by that? I thought the child is going to define the variables again.
Well, when you compile after compilation, your C program is just a bunch of instructions in memory that live in RAM. And so those can be copied because they're just bytes living in RAM. Those can be copied somewhere else. And with appropriate tricks having to do with setting up a sort of virtual memory mappings and make the mappings look the same when the child is in the parent, you can just copy the parent's memory image to the child and execute it in the child. I mean, even though we're looking at C programs, you should think of them as just a bunch of machine instructions, which are just bytes in memory that can be copied.
If a parent has multiple children, would wait just return as soon as the first child finishes, meaning that there could be some more interleaving with the parent and unfinished children? Would there need to be multiple separate waits to ensure all children finish?
Yes. If you call fork more than one, if a given process calls fork twice, then and it wants to wait for both children, it has to call wait twice. And each call to wait will return as soon as one of the children exits. So when wait returns, you don't necessarily know which child has exited, but wait returns the child's process ID as its return value, so you can tell after wait returns, which one it was that exited. As a final example, I'd like to show how all of these facilities combine to implement I/O redirection. So if you remember, the shell provides us with this handy syntax. I can say echo hello greater than out, and that runs the echo command with that argument sending its first, that sends its output to the file out, and we look it out, or better yet, run the cat command with its input connected from the out file. We can see that saved output from the echo command. The way the shell sets this up is as follows. The shell first forks, like on line 13, and then in the child, the shell changes the way the file descriptors are set up so that the child's file descriptor 1, which by convention, most programs use for their output, the shell changes the child's file descriptor to 1 to refer to this output file, and then runs whatever command you wanted. And that leaves the parent shell's file descriptor 1 unchanged. So this idiom of forking and in the child changing around the file descriptors is the usual way in Unix to sort of redirect input and output for a command that you run, but not affect the input and output for the calling program, because we don't want to redirect the shell's output. We only want to redirect the child program's output. Anyway, the way this works, we call fork in the usual way. Line 15 only executes in the child. The reason for the close 1 on line 15 is that in this program, we're redirecting just the output of the echo command. So when I run this redirect program, it produces no output itself, but it ran echo with this output directed to output.txt. So when I look at output.txt, I see this expected output. The reason for the close 1 on line 15 is that we want 1, the sort of conventional output file descriptor, to refer to something else. It happens, so we don't, in the child, we don't want to use the file descriptor 1 that the shell had that's connected to the console. The call to open on line 16 is guaranteed to return 1 because the semantics of open are that open returns the lowest file descriptor number that's not currently in use in the calling process. Since we just closed 1 and file descriptor 0 is still connected to the console, that means open is guaranteed to return 1. So after the line 16, file descriptor 1 is connected to this file. And when we exec echo, echo just writes its output to file descriptor 1, and now it goes to this file. And the cool thing about this is that echo had no idea what's going on. Echo doesn't need to know about IO redirection at all. It just writes its output to file descriptor 1. Only the shell knows about IO redirection. This example also illustrates this sort of kind of neatness of the separation between fork and exec. The fact that fork and exec are separate system calls, so it's separate functions, means that there's a period of time in the child between when fork returns in the child and exec, in which we're still running the calling process's instructions. So the calling process, even though its instructions are running in the child, it's still the calling process's instructions that are executing. And so the calling process is still able to change things, still in control up until line 19. And this sort of interval between fork and exec gives the shell a chance to change what the file descriptors refer to, for example. Any questions about this redirect example? All right, we're about out of time. I'll just wrap up. We looked at Unix's, a bunch of the interfaces to Unix's IO and process abstractions. A thing to take away from this is that the interfaces are relatively simple. You just pass integers like file descriptors and process IDs back and forth across as arguments to these system calls. But sort of the functionality inside the interfaces is relatively sophisticated, like creating new processes and copying the current process. And furthermore, I showed some examples of ways in which the abstractions, though individually simple, combine in useful ways, and for example, to produce IO redirection. There's a lab due at the end of next week, and that lab involves writing more simple utilities like the ones I showed that use the system calls that we discussed. So have fun with that lab, and we'll see you in class next week. And that's it.
Since I'm the one recording, how do I end this? The first time recording is in lecture.
I think when we exit.
Okay. And nothing special, I can just exit and it'll be saved somewhere?
Yes.
Awesome.
Zoom will create some directory and stick the file in that directory.
There's also office hours right after this, right?
Yes.
Perfect. Okay. Cool.
All right.
All right.
Thank you, and I'll see you next week.
Thanks.